So here's a story I read a very long time ago. A major fast food chain had a promotion on third pounder patties, and they were priced very favorably compared to the quarter pounders. And so what do you think happened? Do you think it caught on? So no, it didn't. And of course they got some feedback from some of the prospective customers, and the response they got was pretty consistent. Namely, the third pounders are more expensive, but four is bigger than three. So I got the quarter pounder. All right. So before we blast the American school system, for this reason, consider the following. Suppose the deal had been on half pounders, not third pounders, but half pounders. Say 50% more than a quarter pounder for a half pounder. Now, how many people do you think would have been confused by that versus a third of a pound? So this takes us to some more subjectivity when it comes to numbers. And this time it comes down to, well, I can explain it in one word. Digits. We have 10 of them. Now, like imagine just, for instance, suppose we were like most cartoon characters with, one fewer. We probably wouldn't count all the way up to 5 on a hand, would we? In fact, probably maybe 8 total, not 10. And imagine when those cartoon characters got computers and they're working in base 2 binary, and it just so happens that 8 is a power of 2, cubed to be precise, which means 3 bits of binary is 1 digit for someone with 4 fingers on each hand. We could go the other way as well. Suppose that most people had not 4, not 5, but, well, 6 fingers on each hand. Well, now why stop at 5? You can count one more. And we could either do 6 or we could go all the way to 12. And it just so happens that both of those numbers are divisible by 3. Thirds, not too bad. So needless to say, this does and would change a lot of how people work with numbers, what the numbers look like, which numbers look the more familiar, cleaner. And to this end, I'm just going to show you all some multiplication tables I wrote up and some, a little bit more stuff just to give a flavor of it. All right, here we go. So base 2, 4, 6 multiplication tables and base 8 down here. I skipped the odd numbers because, well, you don't really need those. So base 2, binary multiplication table, pretty straightforward. If there's a 0, it multiplies to 0. If they're both 1s, they multiply to 1. It's an AND, basically. It's an AND logic gate. They both have to be on. But, moving on to base 4 without the computation analogies, here, well, and I skipped the zeros here as well. We have 1 times 1 is 1, so forth. 2 times 1 is 2. 2 times 2 is, that's a new one if you're not used to base 4. This is 1, 4, and 0 ones. So that's what it means to represent it in a base other than 10. We group them once we get to 4, not 10. Just when we get to 4, that's a whole group right there. And then we can keep going. So 2 times 3 is 4 and 2. 2 times 4 is 2 fours. And we get something similar going on here. And again, reminder, when you see 2, 1, that's 2 fours, 1, 1. So 3 times 3 is 2 fours and a 1. Now, once we get to base 6, you get more going on. And this time I skipped the 1s as well to save space. And base 6 is kind of nice, actually. So we've got a lot of patterns. 240, 240 for twos, 30, 30, 30 for threes, a lot like five. It's really a lot like fives in just base 10. Fours are basically every other one of these, so 420, 420. And fives are fun. Note here, actually, I'll get back. So note 1 plus 4 is 5. 2 plus 3, 5. 3 plus 2, 5. 4 plus 1, 5. And if you're familiar with multiples of 9, this will be familiar. 18, 27, 36, they all add up to 9. And oh, these all add up to 3. And this adds to 1. So 2 minus 1, 4 minus 1, 6 minus 1. And we can check the bottom line of base 8. They all add to 7. So some things are pretty much exactly the same. It's just where you put them. So base 6 is pretty nice. I like base 6. Base 8, not too bad, but you have some similar patterns here. The 2 is similar. The 4, well, that's just our half of 8, so it's 04, 04, 04. Although you might notice that 3s and 5s are a bit all over the place. It's kind of like 3s and 7s in base 10. So 6s are okay. And of course, we got this nice little thing with the 7s. So right off the bat, we can see that a lot of numbers, well, they look different. They literally look different depending on what 10 means. And so that's the multiplication part. And so base 12, by the way, also very fun. Trouble is, well, we only have 10 digits that we're used to, 0 through 9, and we need 2 more to work in base 12. And, I could pick A and B or whatever, but it would be a whole extra thing. Suffice to say, it's similar to base 6, except for the 5 and 7s, which are a lot more like these rows here. Now, so that's multiplying. The decimal expansions, or rather, can't use that word, decimal is specifically base 10, but expansions of fractions in different bases are also an interesting thing. Now, on the one hand, some of these things are actually really, really the same. Like if you look at these boxes, for 10, 1/9, 1/10, 1/11. We have this little pattern here. And the same happens for 1/8, centered around, for 8 centered around 1/8, and for 6 centered around 1/6. So it looks almost exactly the same. But other stuff is different. For instance, well, 1/2 is nice in all of them. That's why I picked even bases. 1/3, not too bad in base 10, but not great either. I mean, we don't go out of our way to write anything involving 33.3333%. We tend to stick to things like 20%, 50%, 10%, not a third. In base 6, it's great though. I mean, because 2 times 3 is 6. So yeah, thirds are great. 8 in base 8, eh. And quarters, so 6 and 10s, 6 and 10 work about they work the same, because they're both divisible by 2, but not 4. Whereas 8 is great with quarters, also great with eighths. 2 and 6, a little bit less so on the eighths, but not bad. But we also have some of the not so great ones, like 8 doesn't handle fifths very well at all. And 10 really doesn't like sevenths. 8 doesn't like tenths, and neither 6 nor 8 likes 11 at all. In these two bases, this requires 10 repeating digits, whereas tenths just happen to have the 10 plus 1 going on right there. So a lot of some similarities, some differences, but one takeaway is it looks different, it feels different, it's a different experience, depending on something as simple as how many of these we happen to have. So the whole, mostly hairless ape thing, is surprisingly relevant to our everyday experience. Now, brief note, historically, not all cultures have used 10. Most most famously, the Babylonians worked in base 60, although there really was a base 10 embedded in the 60. Um, but of course, these days, 10 is the standard, and it ain't changing anytime soon. Now, another place where how we write the number has a way of mattering is so when we talk about decimal expansions, every now and again something weird happens, like this. Now, some of you may be comfortable with this statement right here, but a lot of people aren't. Now, we can do there's simple demonstrations for why this works. Here's one. You take the 0.9, you multiply by 10. You move the decimal place by 1. Now you have 1 copy, which you subtract from 10 copies, leaving 9 copies with none of this left. 9 of them's 9, one of them better be 1. But that's not convincing to a lot of people either. And after all, well, 3 reasons. Let's just consider 3 reasons. One, why are we writing this 2 different ways? I mean, it's not supposed to be, what's up with that? We're not, every time, everything we've learned up until this point is utterly incompatible with this. 2, why can't it just be a number that's just a teensy little bit less than 1? It's 9999, so, why isn't there like a 0.00001 that is just a tiny bit different? And 3 is that our squishy ape brains just didn't evolve for this. So I'll just address points 1 and 2. One is, well, by now you may have noticed that there's nothing special about a decimal expansion. And as for point 2, it just so happens that the real numbers, I'll get back to the word, but the real numbers are tailor-made so that it has to work that way. There can't be any tiny little differences that are smaller than anything small. There are no infinitesimals in the real numbers by design. But that means we're going to have to table a lot of this until we talk more about the real numbers, what they actually are. So, brief takeaway just for now is kind of like with the thirds. Yeah, it's to be expected that this is going to be a little weird to people. Fun fact, last time I checked, Wikipedia has an entire article on the general confusion about this one equation. So now a little bit more about, just a bit more about representing fractions is it doesn't have to be an expansion base anything. So I mentioned a little something last video related to the golden ratio and some interesting stuff about it. And that thing is called a continued fraction expansion. Now, the way this works is, so let's suppose we have a fraction here. Well, first, like with anything else, we take away the integer part, and here's what's left. And then, this is where it gets a little interesting. We take this and we flip it. So we flip it, we put it below in the denominator. And then we do this again. 11 over 9 is 1 and 2/9. And then we flip it again. And then we do this again. And this time we get, the 9/2 is 4 plus 1/2, and we're done. So this is where we get to stop. So this is the continued fraction expansion of 42 over 11. We can compactify it by only looking at these things other than the 1/overs. We write, so we have integer part and then these bits. And So first of all, first thing to note about why we would even do this is it didn't matter what base we used. I mean, yes, we're writing these out in base 10, but if we did the whole thing in base 8, I mean, the numbers would look different, but we'd have this, and all of these numbers would be the same. In fact, in base 8, they are the same. These are all smaller than 8. So it so yes, we'll write it a bit differently, but fundamentally, it does not depend on how we count things. That's one reason. Oh, and let's see. Incidentally, I don't know if I already said this, but for, rational numbers, they always stop. Of course, not all numbers stop, which brings me to another reason that this is an interesting way to do things. Back to our old frenemy pi. Now, pi has an infinite continued fraction expansion. But just like with decimal expansions, we can always stop at a certain point. For instance, if we stop right here, we just get 3 plus 1 over 7. The 15 and stuff, they don't enter into it. And this gives us the approximation 22 over 7, which is pretty close. I mean, it agrees in the first two decimal places, and the next one's not too far off. The next two are supposed to be 1.15. So it's only like a thousandth and a half off. Not bad, considering we only took one of these, and the denominator is only 7. And if we go a little bit farther, it gets a bit better. So if we, skip the 15 and and note that after the 1, we have a really big number. And if we have the 292, that's like, it's going to be a dot 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 over 1 plus 1 over 292 stuff, which means that's going to be a very small difference. So big numbers here mean you can stop before with a good approximation. In fact, this is going to be a really good one. So we have 3 plus 1 over 7 plus 1 over 15 plus 1 over 1, stop. And this fraction is 355 over 113, and it agrees with pi all the way out to here, 6th decimal place. Yeah, the next two, by the way, are supposed to be 6.5. So it is really close. And again, that's only taking 1, 2, 3 past the integer. So that's the other thing about continued fraction expansions, is that they are literally the best way to find rational approximations for any number. Now, another interesting thing about continued fraction expansions is while only rational numbers stop, it's not just rational numbers that have nice patterns. Like with decimal expansions, only only fractions can stop or repeat. Not so much with continued fractions. Let's look at a couple here. One is square root of 2, which is 1, plus 1 over 2, plus 1 over 2, etc., etc. It's all 2's from there. So square roots, they work pretty nicely. And this golden ratio, it comes back to here, is a very special case because it has this very particular form, you may recall from the last video, is it's equal to 1 plus 1 over itself, which means we can put this here, and this is, again, 1 plus 1 over itself, 1 plus 1 over itself, and we can just keep going forever, which means the golden ratios expansion is 1, 1, 1, 1, 1, 1, 1, and it's just all ones. Now, here's the thing, though, about that. Now, pi had that nice big 200 whatever. Ones are the exact opposite of that. Ones, well, let's look at the first few approximations. All right, so I've written the first few out here. So we have 1, well, that would be 1 plus 1 over 1, 2, 1 plus 1 over 1 plus 1 over 1. Well, that's 1.5, aka 3 over 2. And if we do one more, we go to 1 plus 1 over 1 plus 1/2, which is 1 plus 2/3, also 5 over 3. Now we have 1 over 1, we have 1, we have 2 over 1, 3 over 2, 5 over 3, and if you've guessed that the next one would be, say, 8 over 5, and the next one after that would be, I don't know, 13 over 8. And yeah, so it literally just happens to be the the ratios from the Fibonacci sequence again, which, well, yeah. But here's the thing, because it's all ones, because these are all ones, it means that, well, even after 3 terms pass here, we're only approximating it to thirds. 5 thirds, that's, well, 1 point repeating sixes. And and here's the thing, I mean, the golden ratio is roughly 1.618. After several, terms into the into the expansion, we still only agree to 1 decimal place. Compare that to how things were working for pi, where we got 2 like that and 6 pretty quickly as well, but here it's actually very slow. In fact, because it's all ones, because there's no big numbers like 200 something or even like 15, it's all ones. It means that at every single step, the rational approximation we get of the golden ratio is literally the worst approximation you can get. As a result, the golden ratio is occasionally known as the most irrational number because it is the hardest number to get a to get a good rational approximation of. So that brings us back to all the things spiraling. So essentially, it comes down to, so here's a, it was supposed to be a sunflower, but I started drawing it and it's just like, anyway, it wasn't going well. So here's a circle that represents a sunflower. And suppose you want a simple to encode in DNA way to get all of the seeds spread out so that they don't all get knocked off by a gust of wind, so that there's no resonant frequency, no specific thing that could happen that would just shake it right off. And a good way to do this is to avoid leaving things in fractions. For instance, if you were to put, you know, grow a seed here, turn a third of the way around, grow a seed here, and then over here, and then back over, you'd have a bunch going out this way, a bunch going out this way, a bunch going out this way, and you'd have the same spacing between all of them. That's a good recipe for a resonant frequency, which means shake it all right off. But suppose you have a number that you can go, you can rotate by that amount and by that amount again and again and again, and it just keeps spreading them out so that there's no nice fractions and no, you know, no invitation for wind to blow it all off. Now, maybe if you had a number that was especially irrational, that, arises kind of simply, it might not be too hard for DNA to come up with that one in specifically a way so that it's just turn, make a seed, turn, make a seed, turn, make a seed. And if you're turning by the right amount each time, where it's never going to come into anything close to a nice fraction that would create a resonant frequency, that would be a problem. Well, maybe, just maybe, after a few 100 million years, a few plants would come up with that one. So yeah, obviously that was the much shorter version from a non-biologist's perspective. But so let's just, look back now at what all this was. What we do with numbers, how we interact with numbers depends a lot on how we write them. You know, everything changes just by writing things in different ways. And in particular, it's worth noting that mathematicians have gone through a lot of effort to make sure that each individual number is objectively defined. This number is this number. But but we also have to get rid of some intuition that tells us that some numbers should look like something and that this number is the following, when really it's just a way to write a thing. All right. So, having talked a bit more about the subjectivity of numbers, I think we're now in a place where I can actually talk about building the different kinds of numbers that we see from the ground up. So, next time, for real this time.